Good morning, guys. It's been a while, so we are going to ease back into the content for this class. The first unit or the first section in Unit 3 is going to be a two-part video. We'll have part 1 today, part 2 obviously will be on Friday, and then kind of get you guys going with polynomial functions and how we're going to use polynomial functions in this course. We really don't have a whole lot of content to cover. In this unit, it should be fairly brief relative to what we've been doing. We will probably have our next exam in about a week and a half. So don't get too comfortable thinking that you've got a little time before the next test. Week and a half, maybe 2 weeks, and we'll see our next test. And then we have Unit 4 and the final, and then you guys are done. Before I get going, though, I do hope everybody's doing well. I really have missed seeing everyone. This has certainly been harder than I think a lot of us have imagined. Initially, everybody kind of thought, oh, wow, we get to hang out at home all the time. And that's turned out to not be so fun. So I just am looking forward to seeing you guys hopefully very, very soon. We are going to talk about polynomial functions and models today. We're going to go through 4 examples. And then we'll complete this set tomorrow with the remainder of the notes. But a polynomial function is simply of the form, let me get the highlighter here. It's a sub n times x sub n plus a sub n minus 1 times x sub n minus 1. And it goes on down the line all the way up through a sub 0. Now, don't get too hung up on that distinct mathematical form. Really, if you kind of think about it, what we're saying here is when we have this exponent n, the next term has an exponent of n minus 1, and then the next one has an exponent of n minus 2. And so we're descending the order of powers as we go. What is really important to note is that n is a non-negative integer. So what that means is that n would have to be some positive number, or it could be 0. The reason we say non-negative, I know a lot of times I've had students ask me this, well, why don't you just say it's positive? Well, non-negative includes 0, and 0 is neither positive nor negative, so we would have to say a non-negative integer, and what that would mean is just all the numbers from 0 through positive infinity. And they have to be whole numbers. That's one of the definitions of an integer. And then the domain of every polynomial function is going to be all real numbers. Okay, so every time you have a polynomial, the domain will be all real numbers. Some key things to note about polynomials: the coefficients are going to be real numbers. The leading term is that the number that's in front of that highest degree term is called the leading coefficient. The term a sub 0 is the constant term. And then the degree of the polynomial is going to be the largest power of x that appears, or whatever your variable might be. So whatever the highest power is determines the degree of that polynomial. One other thing to note here is a non-zero constant polynomial function, such as f of x equals 3, or it could be 5, negative 12, whatever it is, has a degree of 0. And we can say that because essentially it's the same as saying 3 times x to the 0 power. Anything raised to the 0 power is 1. So what we get here is 3 times 1, which is 3. So it is a degree 0 polynomial. However, a variation on that is that if the polynomial is just 0, then it has no degree, because it would just end up being, whatever the case might be, it's always going to end up being 0, so it has no degree. With example 1, we're just simply going to determine whether or not these are polynomial functions, and for those that are, we're going to state what the degree of the polynomial is, and for those that are not, we're going to explain why it's not a polynomial. We also want to write each polynomial in standard form, and then identify the leading term and the constant term. So we've got a couple of things that we want to look at on these. For part A, This one is written in descending order of powers. So this is a polynomial. And it has a degree of 3. Because that is the highest power on any of the terms for x. The leading term is the 5x cubed, and the constant is going to be -9. Okay, there's our leading term, there's our constant, and that's all we had to do on that one. For part B, this one is not written in standard form, which means we have to first put it in descending order of powers. So we'll rewrite this as -3x to the 4th plus x plus 2. Now this is in standard form, and we can go ahead and look at it, and we can clearly see that this is a polynomial, and it has a degree of 4. The leading term is -3x to the 4th, and the constant is going to be +2. For part C, we have this square root of x. Well, one thing that we want to remember is the square root of x can be expressed as x to the 1/2. Now, when you first look at this, okay, you see x is raised to a power. However, one of the key components of the definition of a polynomial is that the exponents are non-negative integers. 1/2 is not an integer. It is positive, but it's not an integer. It is a rational number. So this is not a polynomial. For part D, this is a rational expression. We have a polynomial over a polynomial. So this is not a singular polynomial function. So we will not go ahead and evaluate that any further. For part E, this is kind of like the example where we talked about the 0 power polynomials. We can express 8 as 8 times x to the 0 power. So yes, this is a polynomial. It has a degree of 0. The leading term and the constant both happen to be the same thing, which is just simply 8. And then finally we have this last one. Initially it appears to be a polynomial, and in fact it really is, but we need to expand this x plus 1 or x minus 1 quantity squared. So we have the -2x cubed, and then when we do the binomial expansion of x minus 1 quantity squared, we're going to get x squared minus 2x plus 1. Distribute the -2x cubed through that parenthetical term to get -2x to the 5th plus 4x to the 4th minus 2x cubed. This is a polynomial, and it has a degree of 5. And the leading term is going to be the -2x to the 5th, and our constant is 0, because we can just put a plus 0 on the end of that, and we've established our constant value. The next thing that we see here is a table, and it just kind of gives you an idea of what the polynomials look like as we go on up in degree. So no degree would be just the 0 function. If it has a degree of 0, then it's a constant function, which means it's just f of x equals some number. If it has a degree of 1, it is linear, so you're kind of looking at the y equals mx plus b. Degree 2 is a quadratic. Degree 3 is a cubic. Degree 4 is a quartic. Degree 5 is a quintic, and then we just keep going up. And then after we get to quintic, I believe everything after that is just degree 6, degree 7. They don't have special names. Power functions are the simplest of the polynomials. The power function just simply has this one term has a leading coefficient, variable, exponent, and I'll clarify a couple things here in the green box for you. The first one, it says A is an element of the real numbers. So that means our coefficient has to be some real number. That does not mean it has to be a whole number. It can be a fraction. It can be an irrational number like pi. It just has to be an element of the reals. The only other stipulation on that coefficient is that it cannot be 0. Because if A is 0, then the whole thing is 0, and there's nothing, it's no longer a polynomial. And then the final thing, as far as the notation goes, this n with this funky e, and then z and a plus, what that means is that n is an element. Let's see, n is an element of the positive integers. Okay, that z is the mathematical notation for integers. We've used the superscript plus to indicate that it's positive. So n has to be an element of the positive integers. And then we talked about that with polynomial expressions just a minute ago as well. So some examples of power functions are listed right here. The first one, f of x equals 3x, that's a degree 1 polynomial, leading coefficient of 3. The second one is a degree 2 with a leading coefficient of -5. The third one is a degree 3 with a leading coefficient of 8. And then the last one is a degree 4 with a leading coefficient of -5. And what we're looking at here graphically just shows if we have, say, for example, even exponents, our functions will all somewhat resemble the x squared, and you can see that in red on your screen right now. X squared is one of the primary foundations of all the power functions. And then as our exponents go up by even values, you can see the green graph, or actually let's go to the blue one, x to the 4th. We've gone up 2 degrees on the polynomial expression itself, and the graph still looks very similar to x squared. But what we notice is that its vertex is flattening out some. And then when we go up to a degree 8, again, we have a very similar graph to x squared, but the vertex has flattened out even more. And then we're going to notice the same thing with odd functions. When they're going to all kind of resemble a cubic function. If you recall, a cubic x cubed looks like this kind of squiggly s on the coordinate plane. And then so as our degree goes up and they're odd values, they're going to look very similar to this, say x to the 7th. It'll look the same, but what's going to happen is there in the middle, it's going to flatten out a little bit more, just like we see with the vertex on all the even functions. And the more you work with these, the more this will make sense. So here are some properties about power functions. If the function is even, that means it has an even exponent, so 2, 4, 6, 8, 10. The graph will be symmetric with respect to the x-axis. Part 2, the domain is again going to be the set of all real numbers. The range will be the set of non-negative real numbers. That's provided that the graph does open up. Part 3, the graph will always contain the points -1, 1, 0, 0, and 1, 1. And as the exponent increases, the graph is steeper. But for x near the origin, the graph tends to flatten out and lie closer to the x-axis. So we saw that with those 3 representations of x squared, x to the 4th, and x to the 8th. Here is an example of odd degree. We just kind of touched on that a second ago. The red graph is x cubed. The blue graph is x to the 5th. The green graph is x to the 9th. They all have similar properties, but the x to the 5th and x to the 9th, you can see, are flattened out a little bit more around the x-axis. They both still have the arms, one arm going up to the right, one arm going down to the left. We just have a flatter graph in the middle around the origin. So there's your properties of power functions. I won't read through those again. You guys are perfectly capable of reading I hate when people do that to me. So example 2, it just says to use the methods of shifting, compressing, stretching, reflecting, and we can come up with what some of these graphs look like. So I'm going to look at 1 minus x to the 5th. Now let's base that off of the graph of x cubed. So we're just going to, because it's an odd degree, so we're going to base it off of x cubed. And if I reorder this, it's negative x to the 5th plus 1. And if we remember anything about our transformations, the plus 1 shifts that graph up 1 unit. The negative flips it over the x-axis. And that degree 5 flattens it out in the middle. So what we end up with is we have this graph that's been flipped now over the x-axis. That's terrible. It's a little bit flatter and then it turns down. Okay, so it is similar to x cubed. Again, this is a sketch, so don't criticize me. It's not the best, but we can go to. Where'd my mouse go? I'm sorry about that, guys. All right, so let's go to desmos.com and we're going to graph 1 minus x to the 5th. And there's the graph. You can see it's been shifted up 1 unit. I did sketch my arms in the right fashion. My graph is not nearly as pretty as the one that you see on your screen right now, but it gives you an idea of what's going on. And just for comparison's sake, let me put x cubed on there as well. And so there's the graph of x cubed. Then the graph of 1 minus x to the 5th is there in red. So you can kind of see that. And I do encourage you to use Desmos as you go through some of these examples on your own, or as you look at some of the homework problems, or sorry, suggested problems, as you look at some of those, and get a feel for what happens with these graphs. It will help you tremendously when you're getting ready to take a quiz or test. All right, and then we go to the next one. I have 1/2 times the quantity x minus 1 to the 4th power. So we know that it's an even power, so it's going to closely resemble x squared. So let me just draw x squared on here. The minus 1 inside the parentheses shifts our graph to the right 1 unit. And the fourth degree flattens it out at the vertex. And then the 1/2 actually vertically compresses this graph. So now we're going to end up with a graph that is kind of, whoa, I'm having a hard time drawing these today. Kind of flattened out terribly. Again, this is a sketch. I'm trying to do this on a computer and try to talk to you guys, so don't judge me. Let's look at Desmos. Let's first graph x squared, since I've already said that that's what we're basing this graph off of. The next one is going to be 1/2. It was x minus 1, if I remember, to the 4th power. Okay, there's our graph. Yeah, I flattened it out way too much when I multiplied it by 1/2. So it does vertically compress it. I just flattened it out more than I should have. But you can see here we have the graph in green of x squared, and then the graph here in this purple color is the graph of 1/2 times x minus 1 to the 4th power. So when we talk about the zeros of a polynomial, that's just where does that graph cross the x-axis. So if you look at it graphically, it's where the graph crosses the x-axis. If you look at it algebraically, it's where is that function equal to 0. Some of the summary about the zeros. One is that r is a real zero of a polynomial function f. R is an x-intercept, so that's where we're talking about graphically. It crosses the x-axis. X minus r is going to be a factor of f, and then r is also going to be a solution to the function, or to the equation f of x equals 0. So those are the definitions of a zero. And here we're going to kind of put it into practice in example 3 by finding a polynomial of degree 3 with the given zeros. So we want to look at note 3 up here where it says x minus r is a factor of f. We have these three zeros right here. We know that they are solutions to the function, but what we need to do now is go backwards from the solution to a possible function that these may represent. So if we take that step 3 there where it says x minus r is a factor, each one of these numbers here are our zeros, so they are our r values. So we can establish all three factors really quickly. The first one is x minus -3. The second one is x minus 2. And the third one is x minus 5. So what we get there is x plus 3, x minus 2, and x minus 5. These are all factors of the polynomial that we're not sure what polynomial it may be, but we can actually multiply these factors together now to generate a polynomial that has those zeros. So let's go ahead and multiply the x minus 2 times x minus 5. So we have x plus 3 times x squared minus 7x plus 10. And then we'll distribute the x plus 3 through there, and we're going to get x cubed minus 7x squared plus 10x plus 3x squared minus 21x plus 30. And then clean it up by combining like terms. There is our polynomial of degree 3 who has the zeros -3, 2, and 5. So if we took -3 and substituted in for x, this would end up being 0. If we took 2 and substituted in for x, it would end up being 0. So that's how you go about finding the polynomial when you're given the zeros of the function. If a factor occurs more than once, if it's the same factor and it occurs more than once, it's called a repeated zero of f, or it has what we call a multiplicity of 2, 3, 4, 5, however many times it repeats. And we're going to look at that here with example 4, and then we're going to call it a day for now, because then we'll do the second video or the second part of these notes tomorrow. But here, what's nice about example 4, I've already factored it for you. You don't have to worry about factoring it. We just have to apply the zero product property. And we take each one of the individual factors and set them equal to 0. Okay. On the first factor here, we know that x has to be equal to 0. And we can also see that this has a degree of 2. So it has a 0 of 0, and it has a multiplicity of 2. So that means what happens is this graph does something that we're going to talk about tomorrow at 0 that's kind of important based on the fact that it has a multiplicity of 2. With the second 0, when we solve this for x, we get x is equal to -2, and it has a multiplicity of 1 because the power on x is only 1. And then finally we get down to this last one, and what we would have is x minus 1/2. If we solve that for 0, we get x is equal to positive 1/2. The exponent is 4, so this has a multiplicity of 4. And again, there's something special is going to happen there that we will discuss more tomorrow. But really, just finding the multiplicities should be relatively simple. Understanding what they mean is actually even just as easy, but we're going to discuss that in tomorrow's video. I'm looking forward to seeing you guys in our Zoom class tomorrow. Please don't forget about that, 2 o'clock. I did cancel yesterday so that you guys could finish up your test. The test did actually go very well. I was quite pleased with how that turned out. I also realized too, though, that you were probably using outside resources, and I'm not going to say, hey, you can't do that. But anyway, I hope that this is clear. Remember, if you guys have questions, you can always message me on Remind. I'm always trying to make myself as much available as possible. because I've got nothing better to do right now during the quarantine. So you guys have a great day, and I will talk to you soon.